Hello once again, physics friends. In this video, we're going to do some practice with drawing snapshot diagrams and how to describe events from two different frames. Almost all of this course, the relativity portion of this course and relativity in general, is about viewing events from different frames of reference. And so we need to make sure that we're comfortable with the language of how to talk about events from multiple frames of reference. So here's a problem that'll allow us to practice describing events and also drawing diagrams that represent the instant associated with those events. So the problem right here is that Alice we have in a rocket traveling due east at half the speed of light, and then on the ground below there's a tree and Bob and the tree are both at rest on the ground. And we have a scenario where at the instant that the backside of the rocket passes the tree, or aligns with the tree, a laser beam in the rocket fires a photon towards the front of the rocket. And it just so happens that that photon reaches the front of the rocket at the exact instant that the nose of the rocket reaches Bob. Okay, at least that's how we might describe it in Alice's frame. Okay, so we're going to not do any calculations with this problem. We're just going to play the game of how do we describe in paragraph form what Alice would say is happening, and alternatively what Bob would say is happening. And then we're going to draw snapshot diagrams that represent the instant of these two events A and B. And to be clear, the two events that we're talking about is the following. Event A is the instant that the photon is launched from the rear wall, which also happens to be the instant that the back of the rocket aligns with the tree. And our second event is the instant that the photon arrives at the nose of the rocket, which happens to be the same instant that the rocket nose aligns with Bob. Okay, so a reasonable first thing to do here is to make sure that we can draw this snapshot even prior to event A. So the first thing we're going to do is draw the ground, right? And we know that we have a tree on the ground. I'm drawing the tree that I learned how to draw when I was about 6 years old, and I still don't know how to draw a tree anyway but that. And we also have Bob on the ground. And neither Bob nor the tree are moving. Okay, I'm going to slide this picture over a little bit. And then the other thing we have is, of course, the rocket that's carrying Alice. And we're told that the rocket is traveling due east, and I'm just going to use this simple shape to represent the rocket. And we have Alice on the rocket. I'm going to draw her here just for completeness. And let's say that we're going to draw this, let's say that this is a Bob frame or ground frame representation. So anytime I draw a snapshot diagram, I'm going to want to label the frame. So we'll call this Bob's frame. And I like to just enclose that in a square so that every diagram is labeled. In Bob's frame, Bob is at rest. And Bob and the tree are at rest relative to each other and relative to the ground. So the tree and Bob in this diagram have a velocity of 0. The rocket, however, is not at rest. The velocity of the rocket relative to the ground is half the speed of light, we're told, or 0.5 feet per nanosecond. Okay. For the purposes of this problem, we're not going to actually do any calculations, so the number here is not critical. It just, I want to identify what's moving and what's at rest. Okay. Now, this is not the instant of event A, nor is it the instant of event B. This is just prior to either of those two events. But I just wanted to draw it in this way so you get a sense for kind of the symbols that we might use. Well, now let's think about how Bob might describe this sequence of events from his frame of reference. Right, so we're asked to write two brief paragraphs, one from Alice's point of view and one from Bob's. I'll do Bob's, and then you can do Alice's. So we want to make sure we capture the relevant event in the description, and we also want to make sure that everything really is written from Bob's point of view. And remember, in Bob's point of view, he's at rest, the tree's at rest, and the rocket is moving, and the photon is moving. So here's something that Bob might say. Okay. A rocket approaches me rapidly from the west, At the instant that the rear of the rocket reaches the stationary tree, a photon is launched from the rear wall of the rocket. The photon travels at the speed of light toward the rocket nose, and the photon reaches the nose at the same instant that the nose reaches me. So notice all of the verbs of action are tied to the moving object. That would be the photon or the rocket. So for example, the rear of the rocket reaches the tree, okay, because the rocket's moving. The photon is launched and the photon travels at the speed of light. The photon reaches the nose at the same instant the nose reaches me. So it's the nose that's moving, the photon that's moving, and the rear of the rocket that's moving. The tree is not moving and Bob is not moving. Okay, so now you should use that same idea and write a paragraph from the point of view of Alice. And remember, in Alice's frame, the rocket is at rest and she's at rest, but the tree and Bob are moving, and so is the photon. So pause here and write your paragraph. Next, we're going to practice drawing snapshot diagrams that represent events A and events B. And we're going to do this from Alice's frame and Bob's frame. Well, I'm going to do it from one, and then you can do it from the other. Since we describe the motion in paragraph form from Bob's point of view, I will draw the diagrams from Alice's point of view and let you do the Bob frame diagrams. So we'll start out just by dividing the page, and on the left side, I'll call Alice's frame. And I'm going to do those diagrams. And on the right side of the page, we'll call that Bob's frame, and I'll let you do that. Okay. So in Alice's frame, we're going to have two different events, right? We have event A and event B. And each of those events has a separate diagram. Okay, so we'll put a little divider in here between events A and B, and above this red line, the picture will be event A, and below will be event B. So for event A, that's when the photon is launched from the rear wall, and that's also when the rocket rear aligns with the tree. So let's see, we have our ground, and we have a tree, and we have Bob. And we have the rocket. And at this instant, this is the special instant where the back or the rear of the rocket is aligned up with the tree. All right. Now I want to annotate this diagram by showing velocities, right? So this is Alice's frame, and in Alice's frame, by definition, that's the frame where the rocket and Alice are at rest, okay? But if we're in Alice's frame, that means Bob is moving and the tree is moving. And in Alice's frame, in Bob's frame, Alice is moving to the right. So by reciprocity, in Alice's frame, Bob will be moving to the left. And he's going to be moving to the left at half the speed of light. But everything on the ground, that's at rest on the ground, is moving at that same speed. So the tree is also zipping to the left at half the speed of light, as observed from Alice's frame. And just to be super clear, right, we're drawing this instant where the rear of the rocket aligns with the tree. So I'll indicate that with a dotted line. And at this instant, we release a photon from the rear wall shooting towards the nose. So we're going to use this symbol a lot. A dot and an arrow is going to represent an object that's moving. In particular, that's usually going to be a photon. And our photon diagram will just be a dot with an arrow through it, the arrow indicating the direction that the photon's moving. The velocity of the photon in any frame is always going to be the speed of light. Okay, so we can label that there. Eventually we're going to stop making that label because it's always going to be the same. It's always going to be the speed of light for a photon. Okay, great. So that's one frame of reference. That's one event, but we want to also draw the other event that happens, event B. And recall event B is when Bob arrives at the nose of the rocket. So I'm just going to extend this diagram, this dotted line down to connect points from one snapshot diagram to another. And anything that has zero speed has to be in the same place in both of these diagrams, right? So the rocket has zero speed and Alice has zero speed. So the rocket hasn't moved. and neither has Alice. Now let me draw this a little more accurately. So I'm going to give myself a little guideline here. The nose doesn't move either. So I need to draw my rocket so that the nose is in the same place in both diagrams. Alice is in the same place in both diagrams, still with a velocity of 0. But the photon is moving, and this is a special instant of time. That's the instant that the photon has reached the nose of the rocket. Okay. But it's also special for another reason. It's special because it's the instant that Bob also reaches the nose of the rocket. Okay. So here we have Bob, who's still moving at half the speed of light. Okay. But now he's further to the left than he was in the first diagram. Draw the line of the ground. And the tree, of course, has also moved to the left. And the tree, just to be super explicit, continues moving at half the speed of light. Okay, so if we look at this diagram, we have a few key points. Objects that are stationary in this frame, Alice's frame, have to be in the same orientation, the same location across diagrams. So the rear hasn't moved and the nose of the rocket hasn't moved. Alice hasn't moved. The tree and Bob have moved, so they shift to the left, but they shift to the left by the same amount. And the photon has moved to the right, and it's moved from the rear of the rocket to the nose of the rocket. Okay. Now, if we were to be super accurate, since the photon is traveling twice as fast as Bob and the tree, then this distance that the photon travels in the diagram should be twice as much as Bob traveled. The way we've drawn it, this length that the photon has traveled between the two dotted lines, the green dotted lines, is roughly the same in this diagram as how far Bob traveled. So that's not quite drawn to scale. For the purposes of making this diagram, though, that's okay, and we can indicate their relative speeds explicitly by writing v equals c and half c to indicate that we recognize those objects are moving at different speeds. Okay, so I'll pause there and let you draw out the Bob frame analysis. So pause the video and draw your 2 snapshot diagrams from Bob's frame.